H. Complex numbers. A complex number can be represented by an expression of the form a plus bi, where a and b are real numbers and I is a symbol, with the property that I squared equals -1. The complex number a plus bi can also be represented by the ordered pair open a, b, close, and plotted as a point in a plane called the Argand plane, as in figure 1. Thus, the complex number I equals 0 plus 1 times I is defined with the point open, 0, and 1 close. See figure 1, complex numbers as points on the Argand plane. You have point -4 plus 2i, point 2 plus 3i, point I, point -I, point -2 minus 2i, and point 3 minus 2i. The real part of the complex number a plus bi is the real number a, and the imaginary part is the real number b. Thus, the real part of 4 minus 3i is 4, and the imaginary part is -3. Two complex numbers, a plus bi and c plus di, are equal if a equals c and b equals d. That is, their real parts are equal and their imaginary parts are equal. In the Argand plane, the horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. The sum and difference of two complex numbers are defined by adding in or subtracting their real parts and their imaginary parts. Open a plus bi close plus open c plus di close equals open a plus c close plus open b plus d close I. Open a plus bi close minus open c plus di close equals open a minus c close plus open b minus d close I. For instance, open I minus 1 close plus open 4 plus 7i close equals open 1 plus 4 close plus open 1 -1 plus 7 close I equals 5 plus 6i. The product of complex numbers is defined so that the usual commutative and distributive laws hold. Open a plus bi close open c plus di close equals a open c plus di close plus open bi close open c plus di close equals ac plus adi plus bci plus bdi squared. Since I squared equals -1, this becomes open a plus bi close open c plus di close equals open ac minus bd close plus open ad plus bc close I. Example 1. Open -1 plus 3i close open 2 minus 5i close equals open -1 close open 2 minus 5I close plus 3I open 2 minus 5I close equals -2 plus 5I plus 6I minus 15 open -1 close equals 13 plus 11I. Division of complex numbers is much like rationalizing the denominator of a rational expression. For the complex number z equals a plus bi, we define its complex conjugate to be z bar equals a minus bi. To find the quotient of two complex numbers, we multiply numerator and denominator by the complex conjugate of the denominator. Example 2. Express the number -1 plus 3i over 2 plus 5i in the form a plus bi. Solution: we multiply numerator and denominator by the complex conjugate of 2 plus 5i, namely 2 minus 5i, and we take advantage of the result of example 1. -1 over 3i, -1 plus 3i over 2 plus 5i equals -1 plus 3i over 2 plus 5i times 2 minus 5i over 2 minus 5i equals 13 plus 11i over 2 squared plus 5 squared equals 13 over 29 plus 11 over 29i. The geometric interpretations of the complex conjugate is shown in figure 2. Z bar is the reflection of z in the real axis. We list some of the properties of the complex conjugate in the following box. The proofs follow from the definition and are requested in exercise 18. Properties of conjugates. Z plus w with the bar over it equals z bar plus w bar. And bar over z w equals z bar times w bar. And z to the of a bar over z to the power n equals z bar to the power n. The modulus or absolute value, the absolute value of z of a complex number is z equals a plus bi is its distance from the origin. From figure 3, we see that if z equals a plus bi, then the absolute value of z equals the square root of a squared plus b squared. Notice that z times z bar equals open a plus bi close open a plus bi close equals a squared plus abi minus abi minus b squared. I squared equals a squared plus b squared. And so z bar times z bar equals the absolute value of z squared. This explains why the division procedure in example 2 works in general. Z over W equals Z W bar over W bar equals Z W bar over the absolute value of W squared. Since I squared equals -1, we can think of I as a square root of 1, but notice that we also have open -1 close squared equals I squared equals -1, and so -I is also a square root of -1. We say that I is the principal square root of -1, and write the square root of -1 equals I. In general, if C is any positive number, we write the absolute value of -C equals, I misspoke, we write the square root of -C equals the square root of C times I. With this convention, the usual derivation and formula for the roots of the quadratic equation ax squared plus bx plus c equals 0 are valid even when b squared minus 4ac is less than 0. X equals -b plus or minus the square root of b squared minus 4ac over 2a.